Welcome to Shanti-Peace for Mathematics. In this video, we're going to learn regarding a Lagrange mean value theorem. And the proof of Lagrange mean value theorem is also we are discussing in this video. You can say that the Lagrange mean value theorem is a generalization of a Rolle's mean value theorem. How? Let us see this. So the Rolle's mean value theorem states that let f be a function from AB to R B satisfies the following conditions, that is f is continuous on closed interval AB, f is differentiable on open interval AB, and the third condition is f of A is equal to f of B. Then there exists C in between AB. I should say at least one C in between AB such that f dash of C is equal to 0. Now, what is it geometrically? This Rolle's mean value theorem states that if you have your x-axis and y-axis, and if you have any curve which is continuous and differentiable and is a curve of a function, that means it is a continuous, that means we have 2 points in between that, there is no break. Differentiable, that means every point has exactly one tangent, or I can say it is a smooth curve. And the third condition tells you that both these points are on the same horizontal line. So that means this is the situation. This is my A comma f of A, and this is B comma f of B. And you can plot any curve joining these 2 points, which is a function as well as the continuous function and the differentiable function. So let's say this is the curve I am plotting. Then as per this theorem, it says that you will have always one tangent. At any point you will have at least one tangent which is parallel to x-axis, or I can say it is a parallel to this line, that is a line joining this A and B. So that is the tangent we have here. It is this. So, and this one is another one. So just see that this is touching this thing. So this is my point C that we have, C comma f of C, and at this point the f dash of C is 0. So that is the meaning of a Rolle's mean value theorem. Now in the Lagrange mean value theorem, or how we can generalize this theorem, what I am removing this condition from this Rolle's mean value theorem. That means what I am asking you is, you have some x-axis and y-axis, and you have given 2 points. Now that 2 points are not on the same horizontal line, because f of A and f of B is not same. So that maybe one of them is here, another one is maybe here, we don't know. Now you can join these 2 points with continuous differentiable function. That means the curve might be of this type, maybe the curve will be this type, or it's not properly curve drawn, so I'm just drawing with the proper manner. So let's say this is my curve, curve of the function. This is continuous as well as a smooth curve. So it is continuous and differentiable curve is there, because there is no corner. Now what we can obtain here, if I drop that condition, that means here what we got is one tangent. That means this is my line, this line, the slope of this line, that is this point is A comma f of a, and this point is b comma f of b. Now what is the slope of this line? Is f of b minus f of a upon b minus a. That is the slope of this line. And we get one tangent which is parallel to this line, which we got from here. It is this. This is the tangent which is parallel to this line. And at this point, let's say this point is a C point. This is the C. So this point is C comma f of C. At this point, a slope of this line is f dash of C. And since the slope of these two lines are parallel, so slope will be equal. So we can have f dash of C equal to this. So in the Rolle's mean value theorem, what we have is f dash of C is 0. Why? Because this line is parallel to x axis and the slope of this line is 0. So that's why f dash of C is 0 here. And here, instead of that, we got f dash of C is equal to f of b minus f of a upon b minus a. So this is the Lagrange mean value theorem, it says. So let me state what is the statement for the Lagrange mean value theorem. And we are dropping one condition from the Rolle's theorem, that is f of a is not equal to f of b. Every other things will stay as it is. That means let f be a function from ab to r, where ab is the interval, b satisfies the first condition, that is f is continuous on closed interval ab. In second condition, that f is differentiable on open interval ab. Then there exists at least one C belongs to AB such that f of b minus f of a upon b minus a is equal to f dash of C. So this is a Lagrange mean value theorem, it says. Let us try to prove this theorem. To prove this theorem, I am just doing some rough work here, because we are going to use a Rolle's mean value theorem to prove a Lagrange mean value theorem. So if you want to apply a Rolle's mean value theorem to prove this one, then you need to find out the one function whose derivative is 0 at some point. Here I have given that this is the things we need to prove. So this is the things that I am doing a rough work, that I need to prove that f dash of C equal to f of b minus f of a upon b minus a, that we need to prove. So ultimately I have to prove that f dash of C minus f of b minus f of a upon b minus a is equal to 0. That means I need to calculate some function whose derivative is this. So I can apply the Rolle's mean value theorem for that. Now, how to find out that function? Instead of C, I can just put that f dash of x, because I need to find out the function. And this value, I can say it is a constant value. So I'll just put a here. Now I need to calculate some function which gives you this things, whose derivative is this. So I take the integration both sides, and if I take the integration both sides, the integration of f dash of x will gives me fx, and the integration of ax will gives me minus ax. But this a is also, I am mixed up with this a, because a is a constant, so I just write down, instead of minus a, I just write down plus a. So if you take the derivative of this function, will gives me this one. So I will proceed for starting with this function as my some function whose derivative is this, and apply the Rolle's theorem for this on this function. So to prove the Lagrange mean value theorem, So we'll starting with the proof now. We have to define the function phi from AB to R as phi of x is equal to f of x plus ax for all x's between AB. How we got this idea? We got this idea from this discussion that we have did. Now what we have to check? We have to check that this function phi will satisfy all the conditions of Rolle's mean value theorem. And we are taking this value of a, where a is a constant to be determined. So we can calculate this value of a such that, because I need the Rolle's mean value theorem condition, that is phi of a is equal to phi of b. The third condition that we require, this. So I am calculating this a in such a manner that it will satisfy this condition. So let us calculate what will be the value of a. Due to this, the phi of a is f of a plus a into a, and phi of b is f of b plus a into b. So this will gives you f of a minus f of b equal to a into b minus a. So therefore this will gives me a equal to minus of f of b minus f of a upon b minus a. So this is the value of a we have. Now we note that the phi is a continuous function on closed interval AB, as f is continuous on closed interval AB, because we have given into the statement that f is continuous, and the function phi is f of x plus a into ax. A into ax is a polynomial function, so it is a constant function, and phi of x is also continuous, so that's why both of them are continuous. So sum of continuous function is continuous. According to that, this phi is continuous. Also, phi is differentiable on open interval AB, as f is differentiable on open interval AB. Again, by the same argument, ax is a differentiable as it is a polynomial function. F is a differentiable function. It is given into the Lagrange mean value theorem. That is our hypothesis. And a sum of two differentiable function is differentiable. So this phi function is differentiable. So this phi is satisfying the first condition of the Rolle's mean value theorem, second condition of Rolle's mean value theorem, and phi of a is equal to phi of b. That we already have, because we have chosen our value of a in such a way that this phi of a is equal to phi of b. So what we can say from this, we can say that therefore, thus this phi satisfies all the condition of Rolle's mean value theorem or Rolle's theorem, and therefore applying the Rolle's theorem, what we can say, therefore there exists at least one C in between AB such that phi dash of C equal to 0. But what will be the phi dash? Phi is the function we have. Phi of x is f of x plus ax. So phi dash of x will give you f dash of x plus a. So this will give you therefore 0 equal to phi dash of c equal to f dash of c plus a, and therefore this will give me f dash of c is equal to minus a. But the value of a we have obtained it is minus of f of b minus f of a upon b minus a, and that minus minus become plus, so that will imply that f dash of c is equal to f of b minus f of a upon b minus a, and that proves the Lagrange mean value theorem, which state that if f is continuous on a closed interval AB, f is differentiable on open interval AB, then there exists at least one c in between AB such that f dash of c is equal to this. Now there is another form of the Lagrange mean value theorem is there. So instead of b, if I take a plus h, that means let f be a function from a to a plus h to r be satisfies the first one, f is continuous on closed interval a to a plus h. Second one, f is differentiable on open interval a to a plus h. Then there exists at least one c in between a to a plus h such that f of a plus h minus f of a upon a plus h minus a is equal to f dash of c. But what is this a plus h minus a? It will give me h. Now what is the value of c we have? The value of c is between a to a plus h. So we'll need to modify this statement. So your value of c is between a to a plus h. If I subtract a from both sides, then this will give me 0 less than c minus a less than h. And if I divide by h, then it is c minus a upon h is less than 1. And if I call this value as theta, then theta will be c minus a upon h. So the value of c you will have, it is a plus theta h. So instead of what we have in the statement, that at least one c is in between a to a plus h, instead of that, if I can write down this quantity, that is instead of c, if I write down that there exists at least one theta which is between 0 and 1. So instead of that, we can write down theta is in between 0 and 1 such that instead of this now, f of a plus h minus f of a is equal to this quantity will give me h. So it is h into f dash of c. Instead of c, we have this value, that is a plus theta h. So we can substitute that one, a plus theta h. So this is the another form of LMVT. LMVT means Lagrange mean value theorem. That means f is a function from a to a plus h to r satisfies that this two condition, that is continuous on this interval, differentiable on this interval, then there exists at least one theta in between 0 and 1 such that we have this. Now in the next task, that we say that if a is equal to 0 into the previous statement, then the statement will be changed to let f be a function from 0 to h to r be satisfies that f is continuous on closed interval 0 to h, f is differentiable on open interval 0 to h, then there exists at least one theta is in between 0 and 1 such that what we get as an output, it is instead of a we have 0 here, so it is f of h minus f of 0. So we have f of h minus f of 0 that I will take on the other side, f of 0, this is 0, plus h into f dash of theta h. So this is the another form of LMVT for the interval 0 to h is there. Now let us see what is the geometrical interpretation. Geometrical interpretation of LMVT. So geometrically, let C be a curve of a function joining points a comma f of a comma f of a, and b comma f of b. If it satisfies the two conditions, first one, the graph of C is continuous, or I can say without break, from A to B. The second condition, the graph of C is a smooth curve from A to B, or I can say there is only one tangent at every point in between A and B. This is another way is to looking at this situation. Then there exists at least one point between A and B, at least one point, let's say that point is C, such that slope of a tangent at C is equal to a slope of a line joining A and B. So that is the geometrical meaning of, geometrical interpretation of a Lagrange mean value theorem. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.